Okay, right. So this is, I have done some introduction for the uh, absorption, and these are the things that you can see for the absorption based on the absorption of gas and nitrogen, argon, krypton, and also carbon dioxide also. But of course, there are so many things that can be absorbed on the surface, not only these gases. But normally, for the absorption process, we are discussing on the absorption of gas on a certain surface, right? Absorption of gas on a certain surface. So why? Because what we are interested is to get the surface area of the adsorbent. By doing the absorption process, we can calculate or can get the surface area of the material or the adsorbent, right? So this is a good for application in catalysis. For example, in catalysis, you want to know the surface area of the catalyst. Let me just make it bigger. Okay, so you want to know the surface area of the materials that you use for the absorption. For example, you want to know what is the surface area of the carbon. You know that people have told you the surface area of the carbon 300 meters square per gram. This is a very large surface area. So how do you get a large surface area with only 1 gram of the material? That sounds strange to you, right? You can get 400 meters square per gram. That is probably 2-3 times the football field, right? For the other material like catalyst, you want to know how large is the surface area of this catalyst, because the surface area will affect the rate of the catalysis. If you have a large surface area, meaning that more reaction can occur on the surface and you get higher rate of reaction. All right, so that is another important thing. When you know the surface area, then uh, you can guess, or you can at least predict that you should get a better reaction or better rate of reaction for a certain substance that you have for the catalyst, or certain catalyst that you have for catalysis. Of course, there are so many other. Let me get my pen out. Oh. So there are so many other material or adsorbent that you can use to get the surface area. For example, pharmaceutical product, carbons, silicas, for example, metal powders, oxide, and so on. So the information that that people are interested to know is the surface area, especially, right? And the other thing is the pore. What type of pore? Whether it is a non-porous, is it the material is non-porous, or the material is has pores, but the pores are in micropores range. We're going to see what is micropores range later, or is it in mesopore range of size? This is the size of pore. Now, is it in micropore size range, or is it in mesopore size range? Okay. So what is pore size? So what is the pore volume? And also the pore distribution and so on. So these are the things that people are interested to know, especially when they do absorption of gas on solid. Okay. For example, you have absorption of nitrogen on adapted carbon. All right. So you're interested to know what is the surface area of the adapted carbon, and for that you have to know also the properties of the nitrogen. Okay. So and then the principle is the amount of gas. What the principle is very simple. If you know the principle is just how much gas absorbed on the surface. How much gas absorbed on the surface. So from the amount of gas absorbed on the surface, you can calculate the area covered. The amount absorbed on the surface, you can calculate the area covered based on the cross-sectional area based on the cross-sectional area of each molecule of the gas that is on the surface, right? So for example, if you've got 10 molecule of gas molecule absorbed on the surface, all right? And then each molecule has like 0.2 centimeter square of cross-sectional surface area, right? So meaning that the surface area that the gas is absorbed is 10 times 0.2 centimeter square. So meaning that it is like 2 centimeter square per whatever amount of gas, per whatever amount of the adsorbent that you are using. All right, so we look into that more into that. Okay. All right, so this is the principle, and then from there you can get also the isotherm. Okay, so what we mean by isotherm, and then from there we can determine the amount for monolayer coverage, which is VM, amount for monolayer coverage. So amount of gas that is covered on the surface which form monolayer, that will give you VM, right? Okay, so and then from there you can get the total surface area as a number of molecule of gas times its cross-sectional area divided by the amount of the adsorbent that you use. That will give you the surface area. Normally, the surface area is quoted in meter square per gram. Okay, so how do we do that? All right, so surface area of regular shaped object can be easily determined from their dimension. So if you have, for example, if your adsorbent is in sphere form, right? So how do you get the surface area of the sphere form? There is a formula to get the surface area of the sphere form. I'm not sure, I don't remember. Pi 4 pi r square, something like this. So you can get the surface area, not the volume. The surface area. We're talking about the surface area. If you have a round shape or a sphere, we can get the surface area. If you have a cube, a regular cube, right? So it is easy for you to get the surface area, because it is just, for example, for if each dimension, each side is d, then the surface area is, what is surface area? Is it d to the power of 3?
Yes.
That is volume.
No, this is volume, right? This is volume. So don't confuse with volume. The surface area, don't confuse with volume. So what you have is there are all, how many surface here? 1, 2, 3, 4, 5, 4, and then you have 6, right? You got 6, so meaning that 6 times d square, right? That is the area of the cube. It is easy to get the area of material like this. All right. But if you have irregular shaped material, irregular shaped materials, for example, material like carbon, even something irregular shape, something like this, it is very difficult to get a surface area. And what if you get the material which has pores, which has internal pores, right? Not only the big pores or macro pores, it has also micro pores inside. So it is even difficult. So what I got to do is you have got to do the adsorption process. You got to do the adsorption process, and you get to get how much the adsorbate or gas that is absorbed on the surface. For example, how much gas gas will be absorbing on the surface inside or the internal surface, the internal area of the absorbent, and from there you can calculate how much the gas absorbed, and from from the amount of gas absorbed on the surface, from there you can get the surface area, right? So as I mentioned just now. So the extent of surface area covered is normally expressed in fractional coverage, as fractional coverage, theta, right? Fractional coverage theta, where theta is number of absorption site occupied over the number of absorption sites available. So theta is V over Vm. So V is number of the site occupied, and Vm is the total the total absorption site that is available. So meaning that if all the surface area is covered, all the area in the certain absorbent is covered, meaning that V will be equal to Vm and theta will be equal to 1, right? So theta will be equal to 1. So this is often expressed as volume of absorbent. So what you can do is just to get the volume, right? So because for gas, it is easier to quantify the gas by get the volume of the gas. So if you know the volume, meaning that at a certain pressure and temperature, volume at certain pressure and temperature, that will give you certain amount of gas. So you know that, right? Because for example, if you have 1 mole of gas, 1 mole of gas, 1 mole of gas at standard temperature and pressure, what is the amount? 1 mole, right? What is the volume? What is the volume of 1 mole of gas at standard pressure and temperature? Anyone?
Twenty-four.
Yes, it depends on temperature and pressure. Some will give 22.4, some give 24, and so on, right? So it depends on temperature and pressure. So make sure that you are referring to certain temperature and pressure, right? For example, at 0 degrees Celsius and 1 atm, for example, the value will be 22.4. If you use a higher temperature, for example, at 25 degrees Celsius, which is the temperature that people normally refer to as the standard temperature and pressure, all right, so it will going to be around 24, I think. But anyway, you can do the calculation. How do you do the calculation? It is easier. Just use PV and RT. P is 1 atm, for example. The P is 1 atm. The T is 25 or 0 or whatever temperature that you want to use, right? So you know what is the value of R and so on. Okay, so then you can calculate how much is the amount of gas or how much is the volume of gas for 1 mole of the gas. So that actually valid for all gas. All right. So when the rate of absorption then, d theta dt is the rate of change of surface coverage. The rate of change of surface coverage and can be determined by observing the change in fractional coverage. Okay. So what you can follow for the absorption of gas is just to follow the rate of the coverage. So the rate of coverage is given by d theta dt, where theta is V over Vm. What is V over Vm? V over Vm is the amount of absorption site occupied over the total amount of the absorption site. Okay, so okay, this is to show you. This is just to show you the how the calculation is done. Okay. All right. Okay. So just now we are talking about the sphere. we're talking about a sphere. What is the surface area of a sphere, right? So, but we are not interested in the surface area of the sphere when for the adsorption process. What we are interested in is the cross-sectional area of the sphere. Remember, the cross-sectional area and the surface area is again different. The total surface area of a sphere is, I'm not sure, what is the formula? 4 pi r, something like this. You can refer to to the formula. But anyway, for the cross-sectional area, if you take a sphere, what is the cross-sectional area? If R, if R is the radius of the sphere, what is this cross-sectional area of the sphere? The cross-sectional area of the sphere is only pi r square. It's only pi r square, right? Because we are referring to the cross-sectional area, remember, not the surface area. If it is the surface area, I think it is 4 pi r, something like this. So please check. Or 4 over 3 pi r, something like this. All right. So, but we are not looking at the surface area of the sphere. We are looking at the cross-sectional area. So, if you transform this to this, where r is d over 2, where d is the diameter of the sphere, right? So then the cross-sectional area is pi d square over 4, right? So that is the cross-sectional area of the gas, of each gas that is absorbed on the surface. So the cross-sectional area of the gas, right? So number of gas absorbed, all right? Number of gas absorbed, say the surface is covered. The total surface is covered. There's no surface that is not covered. So you assume that all the surface is covered. So for example, as you can see here, the surface is covered, right? So the surface are all covered. And as you can see here also on this diagram, right? So the surface is all covered, right? So the space is covered where you can find no place or no space which is uncovered by the gas molecule. So if all the space is covered, then the volume that is covered on the surface should be Vm, right? So this is V equal Vm. This is V equal Vm. So meaning that we can then calculate the total surface area of the material. Okay, so what you have got to do is just use Vm. Get the Vm value, right? So that is the volume of the gas. And then Vm divided by V molar. Vm divided by V molar will give you the number of mole of gas, right? Because one V molar is the volume for 1 mole of gas. This is like 22.4 over 22.4 dm cube over 1 mole, right? So this will give you a number of mole. So number of mole time the Avogadro number will give you a number of molecule, right? So this gives you number of molecule. So N is the number of molecule, right? So so what is the area? Okay, the area then is the number of molecule times the cross-sectional area of each gas. The area that is covered here, this is the area, all right? So this area is then number of molecule of gas times the cross-sectional area of this gas. So this is the N d squared over 4, Vm over 8 over V molar. And then after that, you get the surface area. This is we call as the specific surface area. Specific space area, because we have the space area as area over m, where m is the, what is m? M is the amount of the adsorbent that we use. The amount of adsorbent we use, for example, 1 gram, 0.5 gram, or whatever amount, right? If it is 0.5 gram, then whatever A that we get over 0.5 gram, then we can get the space area in meter square per gram, for example, or in centimeter square per gram. Okay. So the normal unit that people use is meter square per gram. So meaning that when you do the calculation, you have got to make sure that the unit is right. You have got to make sure that unit is right. Unit is in like meter, for example. If it is in nanometer, then you got to make sure what is in meter. For example, if here the D value, right? The D value will be in nanometer or in Armstrong. So you got to change that to meter, right? If it is in nanometer, and so on. All right. So got to be careful in the unit that you use for the for the calculation. And what is the last unit that you should get for this surface area? And for example, for nitrogen, it is even simpler for nitrogen. For example, they have got this formula. You can just times Vm with 4.35, the factor of 4.35, then you can get the surface area for absorption of nitrogen gas on the surface of the substance, right? So meaning that if you get the value of Vm for this nitrogen, then it is just to times that the value of Vm by 4.35. How do we get 4.35? Okay, so 4.35 is obtained from this, right? From this part. Okay, so so you got Vm already there, right? You get Vm there, so meaning that so the rest of the rest 4.35, right? So this is 4.35 times Vm. All right. Otherwise, it is not also difficult to do the calculation. What you got to know is just to know the D value, right? You have got to know the D value. What is the D value? What is the diameter of the gas molecule? What is the diameter of the gas molecule? Not the diameter of the atom, the diameter of the gas molecule, right? So for example, nitrogen N2, what is the diameter of N2? If it is argon, argon is a molecule, an atomic molecule. So meaning that the diameter of the atoms is the diameter of the molecule. So that's for the other gas. All right. So so what is theta? So how do we evaluate the value of theta? So you can see from here, I already mentioned what theta just now, right? So this is absorption on isolated site, for example. So this, in this case, for example, theta is of course the first one. You don't see my pointer there. So for the first one, for this one, for example, right? So the value of theta is of course less than 1. So this is the, for example, you can see that this is in during the start of the absorption process, where not many molecule of gas is absorbed on the surface of the adsorbent, right? So and then after you have gone through, after you went through the absorption process, so you can see more surface is absorbed, and in fact, in the second one, right? So the whole surface is already absorbed, and in fact, this at this time it formed what we call as monolayer. surface. All right, it forms a monolayer. Right. So this is the time where we can use the data that you obtain at this stage to get the surface area of the adsorbent. But as you go further during the adsorption process, so more gas will be absorbed, but it's going to form another layer. It's going to form another layer. Then we say that it's forming multi-layer, right? So you can form another layer of gas like the blue layer on the yellow layer, right? The yellow layer is the first layer, the blue layer is the second layer, and you can have more layers on top of these two layers. You can have like 3 layers, 4 layers, and so on. So adsorption can keep on occurring on the surface of the molecule of gas that has been adsorbed earlier, right? So, and as you go on, the pores is filled with the adsorbate. The pores is filled with adsorbate, and this is the stage where we call as condensation. This is condensation where no more adsorption can occur after that, right? So that is the maximum it can go, right? So that is where the pores are all covered by the molecule, by the gas molecule. And the adsorption will stop there, and then probably people will start doing what they call as what they call as the desorption process. So this is the stage. This is the stage where it has the maximum adsorption. Okay, so if you want to evaluate what's the value of theta, then this is the stage where it has the value of theta equal to less than 1. This is the value of theta 1. And then this is from multi-layer or from a second layer, then theta is equal to 2. And when it is condensed, the theta is more than 2. It is more than 2. Okay. So remember, what is theta? So as you have seen earlier, theta is V over Vm, where Vm is the site that is available, V is the site that is covered by the gas, right? And since we are using gas molecule, so V is taken as the volume of gas, volume of gas molecule that is covered on the surface. And Vm is the maximum amount of gas molecule that can cover on the surface to form a monolayer, right? Not the number of molecule that, or the volume of molecule that is on the surface to form condensation. Number of molecule, the maximum number of molecule is on the surface to form a monolayer. All right, it's a bit of thermodynamic of the adsorption process. Factors that is thermodynamic. We are not learning thermodynamic here, but anyway, I think just a brief on the thermodynamic. What is the delta G value for the adsorption process? The delta G value is negative. If you think this is the adsorption process that is occurring on the surface, right? So nitrogen gas, which is free on the surface, and nitrogen gas absorbed on the surface. Of course, if you take the difference in delta S value will be negative because S value for the adsorbed is lower than the S value for the non-adsorbed, right? So that's why delta S is negative. And because of that, delta H, you know delta H is delta G plus T delta S. Or delta G is delta H minus T delta S, right? So we are interested in getting the value of delta H. So delta H is also negative, and it is exothermic. So the process is isothermic, right? So you can also consider the Lennard-Jones potential. I'm not going to go into detail of this, right? So there is a minimum distance that the gas should approach the surface to form the adsorption, right? So for example, this is where the distance, and this is for example, this is the adsorbate surface, adsorbent surface, and this is the distance from the adsorbent, right? So and then the gas is approaching the surface, and it will reach a minimum energy at certain distance from the surface, and that is where it forms the adsorption, or where it form bond. If you're talking about the bond, where it form bond with the surface of the adsorbate. Right, so you can read more about that. So we already discussed on chemistry option, physics option. I don't want to repeat on that. I think we can skip this also. All right, so we go on to the Langmuir theory. So this is one of the theory that they use to calculate the surface area. We call it Langmuir theory. Langmuir theory. So the theory is based on the adsorption of a monolayer of a molecule on the surface of the adsorbent. Right? So this is the what they call as the assumption made. Adsorption is limited to monolayer. All right. So this has limited applicability to physical adsorption and more suitable to adsorption on the in solution. So if you see that people use more in the adsorption of solution for the Langmuir adsorption process. If you later you will do the SCL. So what you got to do is you got to find paper, and you find paper that is discussing on the adsorption of, for example, metal ions, right? Metal ions or heavy metals on the surface of a certain adsorbent, and the adsorption isotope that you will see that people use is the Langmuir isotope. Okay, so surface force is short range for monolayer adsorption. There's only molecule striking bare surface is adsorbed, right? So the molecule that's striking other surface will not absorb. For example, you can have molecule which strike the surface of the gas, not the surface of the adsorbent, and that will not be absorbed. So that is the assumption made for the Langmuir theory. And the adsorption is localized. What is mean by localized? When it's absorbed, it will not move to anywhere else. So meaning that if you have a molecule, for example, you have got molecule absorbed on the surface, and this molecule will not be moving elsewhere. It will stick there, right? So and independent of the area covered. And enthalpy absorption is independent of area covered, and the surface the coverage is uniform, and the adsorbed molecule do not interact with each other. For example, if we have two molecules adsorbed side by side, right? So the molecule only interact with the surface, not with each other, right? So it only interact with the surface. The adsorption occur only on the surface, and the molecule beside this molecule will not affect the adsorption on the surface, right? So the rate adsorption then is equal to the rate of desorption. This occur when adsorption occur. So at the same time, desorption also occur. Remember that. So adsorption occur, desorption also occur at the same time, and it will reach a stage where both will be in equal rate. The rate of adsorption will be equal to the rate of desorption. Let me get the eraser. Where's my eraser? erase. To erase this. So get on my way. Okay, so the rate of collision of gas and the surface is proportional to P. P is the pressure used during the adsorption process, right? And the rate of desorption will be depend on the amount of the absorbed surface. If you have a large amount of absorbed surface, then the rate of desorption will be higher, right? So the more the molecule absorb on the molecule on the surface, the absorption, the rate of desorption will be higher. While the rate of collision, the rate of the absorption will depend on the surface, the amount of the empty surface. So this will depend on the amount of the empty surface. This will depend on the amount of the absorbed surface, right? So let us see. So what is the amount of empty surface? If of course 1 minus V over Vm, because this is the V over Vm is the amount of the surface covered. So meaning that the rate of absorption will be proportional to 1 minus over V over Vm, and the rate of desorption will be proportional to V over Vm, which is the amount of the surface covered. Okay? All right, that makes sense, right? And then, of course, you got to also times that with the Arrhenius factor, right? So a bit of the thermodynamic I got to involve there, right? So which is the exponent of EEDS over RT for the absorption, and EDES over RT for desorption, right? So and then put all together, and you know that the desorption should equal the desorption, the rate, and you get this equation, right? So you get this equation, and further down, since delta H ADS, delta H of absorption is equal to E ADS minus EDS, so then you get this as the formula. And since okay, so how do you get this to here to here? So you got to do yourself, So since enthalpy of absorption is independent of covered surface, then you can just give a constant. So everything here is constant, right? So everything here is constant. So just equal that to with one constant, and one constant there is 1 over V. So what is 1 over V? 1 over V is K exponential delta H ADS over RT. So you can see that there is a one also constant introduced earlier in the equation, which is K. Right? So so that will because you have got K for the desorption process, you have K for absorption process. So K absorption, K desorption, combine them together, give you 1K, right? Right. So and then so this value K exponential delta H ADS over RT is equal to 1 over B. That is a constant, and then you can then further simplify the equation into this form, right? So these are all what we call as the Langmuir equation. This is Langmuir equation, right? So for the Langmuir at low pressure, right? So if you consider this one at low pressure, so then the your V is just equal to Vm times BP. So at low pressure, you will remove this. Low pressure, because P is small, then 1 plus BP is just 1. So V will equal to Vm BP. So that's happening at low pressure. So meaning that what you can get from here is that you can do one data. You can get one data to get the surface area. So meaning that you got to determine the V value, V at low pressure. If you determine the V at low pressure, then you will get you can already get the surface area by getting the value of Vm, right? Because Vm is just V over Vp. So if you know the pressure, of course you know B. If you know the pressure, of course you know B. Then you know the space coverage. You should be able to get the value of Vm only by getting one data. But normally we don't do that. What we do is we want to plot graph. We want to get what we call as isoterm. So we want to plot P over V over V versus P. P over V versus P. So then from there we can get the what we call as isoterm. Right. So there are the number of type of isoterm that you can plot. This is one type. Okay. So we can also plot Vm. Oh, sorry, not Vm. We can also plot V absorbed versus the pressure. Here we use relative pressure. Relative pressure is the pressure over the saturated pressure. Where is the saturated pressure? The saturated pressure is here, right? So this is where you get the saturated pressure. So the pressure that at which there's no more absorption can occur, right? So that is saturated pressure. So the maximum pressure that can go, right? So meaning that all the other pressure will be relative to that pressure. So meaning that the pressure, the relative pressure value will be from 0 to 1. Will be 0 to 1. Okay. Or we can also plot what you call, this is also isotherm, all right? We can do a straight line plot. You can do a straight line plot of PV versus P. PV versus P, PV versus P. So if P versus P, then 1 over Vm will be the slope, right? So 1 over Vm will be the slope, and this will be the intercept. So you get the slope and you get the steps, meaning that you can already get the value of Vm. You can get the value of Vm from the slope, and you can get the value of B from the intercept. Okay, so you can get both value. Why V value is important? Because V value is related to the thermodynamic of the absorption process, to this energy of the absorption. All right, so this is one of the DIY questions that I want to give you, right? Okay. Please look at these questions. I think you should be able to get this from your notes. All right, so make sure that group 1 has already got these questions also. All right. So you will answer these questions later. So in this question already, the plot is done between P over V versus P, and the Y value, which is the equation for the line, is given. R square is the fitting. R square is fitting. Don't worry about R square. R square is the fitting. What you have to worry about the equation given on the line for the line. So from there you have got to determine the surface area of the activated carbon. So this is the certain plot of carbon dioxide, so carbon monoxide, which the radius given, right? With the radius given, carbon monoxide with the radius given, and it is on 0.1 activated carbon. So what you have got to determine is the specific surface area. Remember what I have told you about the specific surface area, all right? So you got to do the calculation for the specific surface area at STP. So what is STP? You got to find out what is STP. STP is standard temperature and pressure. Okay, so there is more. There are questions that you can do. You can do this exercise. These are all using the Langmuir equation. Okay, because of course you've got more data here, right? You've got more data here, meaning that you have to do the graph. You have got to do the graph. So this is six sets of data, right? So what you got to do is to plot the graph as shown previously. So what you got to do is you got to plot this graph. Okay, so this is the graph that you want, right? From there, you can determine. From there, you can determine the find the value of equilibrium rate constant. Equilibrium rate constant. So what is the equilibrium rate constant? So see from and the adsorption volume. Okay. And then from here, from the second one, what you got to determine also is the rate constant and also this adsorption of volume at complete coverage. Complete coverage means VM. What's the value of VM? So what is the rate constant? That is the value of K that we have seen earlier. All right. So the other theory is on BET theory. This is a bit different assumption, where the assumption is that the adsorption occur by multi-layer rather than monolayer, right? Adsorption occur by multi-layer rather than monolayer. So the equation involved is quite difficult in the derivation, of course, because of that, only the final equation is given here, right? The final equation is given. So you can see the equation is more complex compared to the Langmuir theory, because this is where the assumption made is that the adsorption is not by monolayer, but adsorption occur by multi-layer. So meaning that the adsorption occur in the process, it can go stage by stage from this, right? It can occur stage by stage. The first stage is the adsorption occur, right? So you can see here, the adsorption start occurring, and then it reach a stage where the adsorption occur and cover the whole surface. So this is where you can read the value of VM, and then after that it keep on occurring. The adsorption keep occurring, and form another layer, right? So here where the adsorption form a second layer, and so on, right? So and then you can go on and form layers and layers and layers, a number of layers. So then the adsorption can occur multi-layer. So this is especially good for this physical adsorption process. Physical adsorption process. Many people are using this rather than the Langmuir adsorption process, because Langmuir adsorption process is more relevant to the chemical adsorption rather than physical adsorption. Okay, this BET adsorption is more relevant to the physical adsorption rather than the chemical adsorption. So that's why people are more interested to use this BET isotherm rather than Langmuir isotherm for the case of physical adsorption. So the same thing, you do the plot. So this is one isotherm. You can also plot V adsorb versus P over P naught. You can see the plot is almost similar to that of Langmuir, but the only thing is that we have another stage of adsorption where adsorption can occur by multi-layer. All right. So and then you can also do this linear plot by taking P over P V P naught minus P versus P over P naught. So that will give you the straight line, and you can get slope as C minus 1 over V VMC, and the intercept as 1 over VMC, right? So in slope plus intercept, slope plus intercept will give you 1 over Vm, right? And meaning that slope, you have to use slope and intercept together to get the Vm value, or for the calculation of the surface area, you are interested to get the Vm value. So you want to get the Vm value, or Vm value is equal 1 over slope plus intercept. Also, you can use this value also. So meaning that if you get the value of the intercept, you get the value of the slope, then you can calculate what is the value of Vm. If you are not sure, then go back to the equation, to the equation, and see what is intercept, see what is slope, and from there you can get that also 1 over Vm is equal to slope plus intercept. Right. So once you get the 1 over Vm value, you should be able to get Vm value. Once you get the Vm value, you should get the surface area. When you get the Vm value, you should be able to do the calculation of the surface area. Alright. So this is another DIY. So I've given you 2 DIY. This one, the previous one was 1. I can say this is DIY how many? That's already number of DIY already, right? So probably I label this as DIY 3, for this case. So you have got DIY 1. Oh yeah. So this is DIY 1. And then you have got DIY, so DIY 2 here, DIY 3 here, right? So meaning that this is no longer DIY 3, this is DIY 4. So this is actually DIY 4 for this one. What is DIY? DIY is do it yourself. You have a lot of DIY here in around your place. Okay, you can also do single point BET, right? You can do single point BET. So if you know the this is the equation, right? This is the equation given earlier. Okay, so but usually the intercept is small compared to the slope and may be considered insignificant. Thus, the line may be forced to pass through origin, and this is equivalent of assuming that C is large. So if C is large, then you can also do a 1 point DIY, right, by using this equation. So meaning that assuming C is large, so this is then a 0. So C is large, then C minus 1 is also is equal to C, right? So C will also cut with the C here, right? And then the equation then is reduced to only this form, all right? So it's only reduced to this simple form, right? So meaning that if you know the pressure, right, you can, and you know what is the amount absorbed, you know the pressure, you know what is the amount absorbed, you can then straight away calculate what is 1 over Vm or what is Vm from only 1 point. One data or 1 point. Just now we see also 1 point for the Langmuir. This is 1 point for the VET. So, but this is done normally for the pressure or the relative pressure around 0.3, where C is very large, right? C is more than 100. But if C is less than 80, you could get large error. So it is not recommended then to use 1 point if C is less than 80. If C then more than 100, it is good. Meaning that you can determine the value of surface area at P over P naught at relative pressure of 0.3. 3. Okay, there's a certain P over P naught that you can determine the value of V. So at this P over P naught, determine the value of V. So this value of V will give you the value of Vm. Right? So that is one point. So meaning that you don't have to plot graph. You only determine the value at 0.3 relative pressure, and that will give you the Vm value. So that is just derivation. So this is another DIY. So meaning that this is DIY 5, right? So there's a number of DIY already. Right. So I will not go on to this one. All right. So this is okay. Let me just finish with this only. So this is just showing you this absorption that occur for multi-layer absorption. Right. So this is how the absorption occur on the non-porous and on porous material. On porous material and non-porous material. So the absorption that occur for the porous material, for example, here. So here is where the interaction occur with most energetic region of the solid. Right. So meaning that the solid at that stage is still more area which is unoccupied. So the surface is almost empty at the stage. And then the gas will be absorbed on the surface of the adsorbent. And when it start absorption, when the absorption start occurring, so more and more gas is absorbed on the surface, right? So and then it will start doing the first layer. We start doing the first layer. This is where the first layer occur, and then after that, this absorption also start doing the second layer, third layer, and so on. Meaning the multi-layer absorption start occurring at this stage also. So if you go on further on the absorption process, so then this bulk condensation start occurring, meaning that the pores will start to be filled in with the molecule. Will start to fill in with the molecule and will be accumulated. The pores will be accumulated with the gas molecule at this stage, right? So this is the area that you want. This is the area that you want. This is the area that you want to read what is the value of Vm from the acetone. But this is not only the type of acetone that you can get. You can get also this type of acetone where absorption occur, right? Absorption occur. This is where the absorption occur, right? And then as you can see for the previous one, but when you do the desorption, the desorption occur not following the same line as absorption, right? It following the different line. This is the absorption line. So this is the desorption line. So why does it occur like this? This is because of the energy that is needed for desorption is or the pressure needed for the absorption is less pressure that is required for the absorption process. Meaning that you have to give lower pressure for the absorption to occur. That shows that how strong is the absorption process. If the absorption process is quite strong, or is the interaction between the gas molecule and the surface is strong, then you got to give lower pressure for the absorption to occur. And that will give you what they call as hysteresis. So it's there, no? Right? So this is hysteresis, where there's difference between the line that is for desorption and the line for absorption, that is called as hysteresis. And for this case, there's no hysteresis, meaning that the line of absorption and the line of desorption occur on the same line. Right. So you got hysteresis, one you don't have hysteresis. And one with hysteresis normally occur for material which is porous, one which has no hysteresis occur with the space which is non-porous. Okay, so I'll stop there for the absorption for today. But anyway, this coming test will up to this we will up to this slide. Okay, the coming test, right? So, and then for today, there's a quiz for you to answer. Which one? Okay, this is the one that you need to answer. Very easy questions. Very easy questions, only that you have got to do some calculation and make sure the unit all okay. And what is the value of the specific space area? So the specific space area must be given in meter square per gram. Okay, the specific space area should be in meter square per gram, right? So you may start doing your quiz. You may start doing your quiz, and the time given is from now until 9:59. 9:59. Remember, 9:59. So you got to submit before 9:59 or at 9:59 or before 9:59 actually. Right? So good luck to you. So remember, next week we're going to have tests. Right? So do the preparation and keep track with the Putra Blast, because I want to put few more questions in Putra Blast. So that you can do some a bit more exercise, and not that much. I think probably one or two more questions, especially on the part for the acid-base catalysis, which has less example. All right. Okay. So okay. Is everybody okay? So I can see that you are busy answering the questions. Okay, I hope everybody are okay. So, and then each group can submit to the Putra Blast whatever what is the, I mean, Hanif also has already created this quiz for Putra Blast in group 1, sorry. So you can also submit there for group 1 and group 2. Of course, I already created this quiz in the Putra Blast. You can also submit there. Any questions while you are doing the quiz? Everybody are silent. All right. Okay. Thank you very much. Okay. So see you in the test next week.
Okay, Doctor.
Okay, Doctor.
Thank you,
Okay.
Doctor.
Thank you.
Okay.
Thank you, Doctor.
All right.